All right, it's ready. Please go ahead.
Okay. Hello, everyone. This is first of all, I want to thank everyone for your interest in our workshop. And we have a number of modules that you will be going through, and a number of laboratories associated with each module. This is the very first module. It's the microcontroller technology introduction. And the assumption here is that you have had, if you're interested in this, you have had worked with microprocessors or microcontrollers. Even if you had them some years ago, it will be a review for you. So we are not going to be going too into detail. Now, after each module, you will have the corresponding laboratory. And again, the assumption here is now you have your own PIC platform with one or two chips. In these lectures, we will go over 84A, PIC 84A, but chances are you may have already given 77A as well. And after you are done with this lecture, when you go into the lab, you will actually learn how to program a chip. All the instructions are given, so you will just follow that once you are done with this lecture. Now, let me see. Now, the first thing is just to, as a review, let's take a look at the difference between microprocessors versus microcontrollers. Again, the assumption is you worked with them some time ago. As you know, microprocessor is the typical brain of the computer, but it needs other peripheral devices. Microcontroller, on the other hand, has all the features, all the peripherals needed for someone to actually design an embedded application. So along with the microcontroller, in one chip, you also have memory, I/O facilities, and anything else comes with that particular chip. If you take a look at the brief history of microprocessor development, first commercial microprocessor was introduced by Intel in 1971, and that was 4004. And then came in 72, first general purpose 8-bit microprocessor, 8008. Later, second generation of 8-bit microprocessor, Intel 8080 came. I still have those Intel 8080 books in my office, along with some others, obviously. Then after that, in 74, Motorola introduced 6800. Then the third generation of 8-bit microprocessors came along, such as 8085 from Intel, 6809 from Motorola, and so on. Later, 16-bit and also 32-bit microprocessors came along. Now, one can think that, okay, now that we have the more powerful architectures, such as 16-bit or 32-bit compared to 8-bit architectures, we wouldn't use 8 bits anymore. That is not the case. They do coexist, and actually many 8-bit microprocessors and microcomputers, they have more than adequate power and gadgets, peripherals to do many embedded applications with much lower cost. Next is microcontroller applications, and I don't need to name them all. If we take a look around, we see these applications everywhere, from our washers, dryers, microwaves, cameras. Everywhere you will see microcontroller. But this next example, such as cooking a bag of popcorn in microwave oven, is given, and I really like this. So I'm just gonna go over just in a minute or two. For example, if you have a bag of popcorn and you wanted to make that, you open the microwave door. So the microcontroller, as soon as you open it, it senses the door is open. Then it turns the light on and disables the magnetron. So you put your microwave, you put your bag of popcorn, and then microcontroller starts scanning the keyboard because it's waiting for your input. As soon as someone pushes the popcorn, or whatever, how many seconds you want to do that, or a minute or two, the microcontroller says okay. It confirms the door is closed, starts counting the timing, because if you're going to have it for a minute, 2 minutes, it starts counting the time, starts the motor that turns the turntable and sets the power of the magnetron, and starts controlling the display. When the timer gets 0, microcontroller shuts off the magnetron, stops the turntable, and beeps it so that you know that the popcorn is done. You open the door. Many microcontrollers come with various extra features, such as analog to digital converters, pulse width modulation, watchdog timers, controller area networks, and so on. So whatever your application is, you can pick and choose what kind of microcontroller chip you need to use. Now next, let's take a look at the microprocessor architectures. The first one we'll talk about Princeton or von Neumann architecture. This is a CISC architecture. It's a complex instruction set. In this case, both the memory as well as both the memory and program memory, they coexist in the same address bus, but at different addresses. So as you can see here, if you put your program here, your data is here. You want to make sure that the, for example, program do not overwrite your data, they do not meet, otherwise you'll have corrupted data, corrupted information. Your program is not going to work. So actually this is simple. The architecture is great for number crunching, and if we take a look at this, how the execution happens is you first fetch the first instruction, then that instruction is executed, then the next instruction in line is fetched and then executed, and so on. So it goes in sequentially. If you take a look at the Harvard architecture, that's a RISC architecture, RISC instruction set. That's a reduced instruction set. The architecture is more complicated, but it is faster because of pipelining. So, and this is well suited for control applications. And let's take a look at the why this is faster. First of all, in Harvard architecture, the program memory and data memory, they are in separate places. So therefore, while you are fetching one instruction, while you are executing one instruction, you can fetch the next instruction. So as this example shows, the first instruction is fetched, and then while you're executing the first instruction, you prefetch or you fetch the next instruction. Then you execute the next instruction. While you're executing the next instruction, the next one in line is fetched, and so on. So because memory spaces, the program memory and data memory are different spaces, they could have different sizes. In this case, for PIC family, the PIC platform that we will be using, it has different sizes. So the data bus is 8 bits wide, while the program bus is 14 bits wide. Let's take a look at a little more on pipelining. Again, the pipelining allows overlapping of the fetch and execution steps. And in this example, we have 4 instructions, and we will take a look at these across 5 instruction cycles, what happens at each clock cycle. So every instruction takes 1 instruction cycle, except the instructions that will modify the program counter. What are those instructions? Those are call, jump, or return from subroutine instructions, because they all change the program counter contents. So those instructions will take 2 instruction cycles rather than 1. Now, if we take a look at the very first instruction, this is a move LW55 hexadecimal. This instruction moves the literal to W, and your literal or your data is 55 hexadecimal. So at the end of the execution, W will have 55. So during time T0, this instruction is fetched. And during time T1, while this instruction is being executed, which means that at the end of the execution, W will have 55 hexadecimal, this instruction is prefetched, the next instruction. The next instruction is moves the contents of the W register into the file register. In this case, it's a port B register. So during time T2, this instruction, the second instruction is executed, which means that, remember, at the end of T1, W register had 55, and then that here, when this instruction is executing, that 55 goes into port B, and then the next instruction is fetched. Now, take a look at this. The next instruction, or the third instruction, is a call subroutine instruction. So during time T3, while call instruction is executed, the next instruction in line is being fetched. However, when you have a call instruction, what happens is that in the meantime, the program counter has already moved to the next instruction to be executed, which is here. So, however, you are calling, you want after the execution of this call instruction, the next instruction to be executed is not going to be this one, but it's going to be the first instruction in that subroutine. So what happens is that the program counter will be saved in the stack, which we will see in a few minutes, as your return address, and the program counter will be loaded with the address, beginning address of this subroutine. Sorry. Okay. Let's take a look at this. All right. Now in T4, time T4, what happens is that this instruction doesn't get executed. Why? Because the program counter already is pointing or trying to fetch the first instruction in the subroutine. So this is flushed, flushes the prefetch, fetch, and fetches a new instruction, which is the first instruction in the subroutine. So therefore, whenever you do anything that modifies the program counter, the ALU will automatically flush the instruction which had been prefetched and throw it away. So these, again, the examples of these instructions are jump, call, return. So at the end of the subroutine, you will have the return instruction. When the return instruction then will initiate the saved address, which was your return address, to be reloaded onto the program counter. Now, PIC microcontrollers are based on Harvard architecture, and which we will take a look at the architecture in just a few minutes. Here is the PIC architecture. You have a flash program memory 14 bits, and you have a 13-bit program counter, and the core only implements 1K of the program space. Now, if you take a look at the stack, stack has 8 level deep. That's the hardware stack, and the stack is not used to pass parameters around. However, to store the program counter contents or your return address. The reason we have 8 because that allows you to have nested jumps or nested loops or interrupts. Let's take a look at this. So we've talked about this. Okay, so when you have, so the stack is used to, again, we said to store the program counter, which when you jump to a subroutine, or when you have an interrupt. When you have an interrupt, automatically the interrupt vector address is loaded into the PC. However, if you have a call to subroutine, that address is already a part of the instruction that goes into the program counter. Now, we will follow the instruction move F port B, comma W through the PIC architecture. This instruction will take the contents of port B and copy it onto the W register. Now, because we have the program memory is 14 bits long, the instruction is 14 bits, which goes into the instruction register. Now, the 7 bits is the instruction opcode. So that actually tells what kind of instruction there is. For example, in this case, that's a move F instruction. Then the next bit is the destination code. In this case, destination code is 0. Therefore, the result will go into W register. But if it was 1, it would go into the same register, the originating register. Why do we need that? Because sometimes you need to check set the status bits. So you do that so that the status bits are, you put it back so that while you're doing that, the status bits are set. Now these 7 bits, the least significant 7 bits, define the address of the register where the data to be stored will come from. In this case, the 6 comes from port B. The destination bit, we've talked about that. Okay. Now, if you take a look at this address is the address of the data memory space. And let me see, I think I have an example here. Okay, now again here, this is your instruction register, has 14 bits. These 7 bits goes into the instruction decode, and it decodes and then makes sure that that's okay, that's a move F instruction. Now the address part goes into the address mux. This is the direct addressing. And then here is the W register. W register is the integral part of the ALU in this architecture, and it does not have a separate address space itself. Now, in order to move data in and out of W register, you must go through the ALU. immediate instructions take the 8-bit literal value from the instruction and into the ALU mux, into the ALU mux, and this path then these 8 bits come through the ALU mux and then goes into the W register. Now, if you take a look at the I/O ports, they sit on the same data bus as the file registers. You can address I/O ports and RAM using exactly the same instructions that you would for file registers. So therefore, the contents of port B right here, the contents of port B are copied into the W register. So data will be read from the I/O pins into the data bus, then through the multiplexer, through the ALU, that goes into the W register. Now, if you take a look at the address mux, that requires either direct addressing or indirect addressing. We've talked about the direct addressing, which is a part of the address is a part of the instruction, but the for indirect addressing, the file select register is the indirect data address pointer that has the address of the data. Okay, you can also take the contents of W register and move it into the program counter if you desire. So let's take a look at this. You could also take the contents of the W register onto the program counter. But if you take a look at this, the contents, the database is 8 bits long, the program counter is 13 bits. So therefore, these contents will go into the lower 8 bits of the program counter. We also wanted to mention the status register. Status register is right here, and also sits on the data bus, and it gives the status of the ALU. So if the destination is 1, then the contents will go back into the originating wherever it was before, but the status register is set. So the last ALU operation, such as carries, overflows, and so on, will be shown on the status register. If you take a look at the left side of the diagram, you see a number of auxiliary features of this architecture, such as timer, oscillator, stop-bar timer, Brown-out reset, and so on. And you also see the timing generator block, which generates the necessary timing signals for the device. Now, these signals are derived from an external oscillator, such as external ceramic resonator or an internal RC oscillator. Whatever the source is, the frequency gets internally divided by 4 in order to generate these cycles. So 4 of these make one instruction cycle. So for example, for our PIC platform, we use 20 megahertz resonator in the PIC trainer. So therefore, if you divide that by 4, you will get 5 megahertz for each instruction. And then if you to find the timing, that comes to 200 nanoseconds. Now, the next couple of pages, they talk about different resonators, oscillators, and so on. So you are welcome to take a look at them. And then this page talks about various memory types incorporated in microcontroller design. You are welcome to read them on your own time. Then also the next couple of pages talks about various different chips, and since we are only going to be talking about the 16F84A, here is the information that has, just like we've discussed before, programming flash memory has 1024 words. This is the range, and it has 16 bytes of special function registers, 68 bytes of general purpose registers. And here are the definitions. And then there are different memories. I'm not going to go over, but I'm just mentioning that they are there in case you need to work with them. You can go back and take a look at it. This is another chip that I mentioned before. So that's that's all I will cover here. Now, after this this section, what you will do is you will go into the laboratory section, lab section. You will actually learn how to program a chip. So I will stop here. I want to thank everyone for listening to me.